Okay, class. This is part 2 of the second order systems. Part 1, we covered a brief introduction to second order systems. Part 2 was about behavior. Part 3 was about performance metrics. And part 4 is going to be about the frequency response. Okay. Oops, response. This is going to be pretty short, I think. Okay, so let's just remind ourselves what a first order system looked like. So what I'm going to do is I'm going to plot the two Bode plots here for the phase and amplitude. So that's the amplitude in decibels, let's say, and that's the phase in degrees. Both y-axis are log frequency, of course. For the amplitude, a first order system does that, and the phase plot does something like that. The phase plot reaches an asymptote of minus 90 degrees. Okay. The amplitude plot, it says a slow change, decrease, and then it rapidly drops off once you pass the bandwidth of the system. So that's what a first order system, how a first order system responds. What about a second order system? That's a lot more interesting. So let's do the same plot for a second order system. So the two plots again, okay. That's going to be the amplitude, decibels. This is going to be the phase, and we've got log frequency on both axes. Now, for the amplitude, it all depends what the value of zeta is, right? So if the zeta is greater than 1, you'll get something that looks vaguely like or quite similar to a first order response. Okay, so this is the case when zeta is greater than 1. The minute zeta drops below 1, however, because below 1 we start to get damped oscillations, the Bode plot changes. In fact, what happens is below 1, when zeta is below 1, you get this peaking appearing. Okay, this peak. You get this peak, and this is basically a resonance peak. And this is due to the fact that the system shows damped oscillations. So, for example, this one might be, zeta equals, 0.4 or something, okay? For the phase plot, not as interesting, but for the first order, looks like that. The one big difference, sorry, the second, if zeta is greater than 1, you'll get, it'll look like that. But unlike the first order one, this will drop to minus 180 degrees. Okay. Now, if zeta is less than 1, all that happens is it becomes a bit steeper and does that. So this is the case when zeta, let's say, is 0.4. Okay. So these are the two cases. It's possible to derive equations that measure both the location of the peak and its amplitude. Okay, so the frequency at which the peak occurs, which is omega r, is omega n times the square root of 1 minus 2 zeta squared. Okay. There are some limits on this. You only start this. You only get positive roots when zeta is less than 0.707. Okay. And you only start getting the resonance peak when zeta is actually below 0.707, which is why I put at least zeta 0.4 there. So that's the frequency. The amplitude is given by mr half 1 over zeta, then a square root 1 minus zeta squared. Okay. And here you can see perhaps that, as the zeta gets smaller and smaller, so this value gets bigger and bigger. Okay, then notice the amplitude of the resonance peak gets taller and taller and taller. And you can imagine in the limit, it approaches infinity effectively. Okay, when you get then center-like oscillations. Okay, I think that's it. I think we're done. All right. Okay.